continue to work on inverse functions today. So we'll have day 2 of inverse functions. And make sure project number 3 goes into your the blue folders on your table. Project number 3 in the folders. And don't forget, Monday you have your next quiz, and it's on classes 17 to 21. But remember, class 19 is not new material. Class 20 we did a couple of weeks ago. It was out of order. We did that right after class 16. We did it 2 Fridays ago. Or was it 1 Friday ago? It was the Friday before the long weekend. That's when we did class 20. And what else did I want to mention to you? Your test number 2 will be next Friday, November 1st. And there was one other thing. Oh yeah, midterm grades. I had a student come in yesterday, and she walked out with a list of all of her averages for her homework and her quizzes, her projects, tests, all her individual quiz scores. We created a study plan for the rest of the semester, and then another check-in date. So if you're serious about trying to improve your grade, then I suggest, even if you want to improve it from a B to an A or an A- to an A, I welcome anyone, not just the people that I've sent the early progress reports to, but anyone to stop by, and I'll provide you with the same information. Now remember, Friday, when you take the second test, your first test, if you didn't do well on your first test, that's counting 40% of your overall grade right now. So it's got a very heavy weight. After next Friday, that first test will only count 20%. Okay, so it does not weigh as heavily. So hopefully you'll improve next Friday over your first test, and then your overall grade will improve. If it does not, remember, you then have another week, because the last day to withdraw from a class with a W is on November 8th. So if after next Friday and early of the next week, the 4th or the 6th, you come to see me and things are not looking too good for you, depending on your situation, you may want to just withdraw from the course, but stay in the course. Stay here for the rest of the semester so it doesn't affect your GPA, and you absorb as much as you can. Go through the course one full time and then take it again in the spring. That's often the situation. This is not an unusual situation for 107 students. This is a very common thing for students. And sometimes people withdraw and they just disappear, but it really is helpful to sit through one full semester so you get to see the whole semester. So again, you have lots of opportunity to see me, and I'll work through as much as I can with you, and we can set some plans like I did with this person yesterday. And you know, it's hard. If you're working 60 hours a week, it's hard to take 4 credit courses, right? It's kind of like suicide almost. And that's a situation some students are in. So got to kind of do some time management together, okay? So let's take a look at today's material. And again, we're going to start with a real quick review of what we covered on Wednesday. And so far, our discussion of inverse functions, we've been talking about a finite set of ordered pairs. And we've been talking about swapping the input and the output. And another way to look at that idea is this little visual here, where the domain of your first function in the range of your first function, so you have a particular value in your domain of your first function, let's call it A. It goes into function machine F, and it comes out looking like B. That's the range of your first function. Then what happens with this inverse idea is, remember, we're swapping. So as an ordered pair, this would look like this, A comma B. And we talked about swapping the inputs and outputs. So if we now apply our inverse to B, it takes us right back to A, this round trip idea. So that looks like this. So the input and output swap places. And so we've been practicing this idea with a finite set of ordered pairs. Today, we're going to move beyond a finite set of ordered pairs and look at an infinite set of ordered pairs, which would be like an equation like f of x equals x plus 1 or x squared plus 2, where we have a mathematical equation. The other idea that we highlighted, and some of you rolled your eyes when I did the really big show, is that to verify, and I won't mention who, but I saw you. I saw you, Austin. No. The next thing we're going to do is to say that if we have two functions and we're trying to show or verify that they're inverses of each other, how do we do that? We compose the functions and we reverse the order. And if we do that, we come right back to x. And if that happens, if we compose both the functions, if we compose f and g and we reverse the order and both of these compositions take us back to x, then they truly are indeed inverse functions of each other. Okay. So today we're going to work on a couple of different ideas. Some of them are visual ideas. How do we know from looking at the graph of a function whether it has an inverse function? If I have the graph of a function, how would I draw its inverse function? And if I have the equation of a function, how do I mathematically create its inverse? So that's what our job is for today. So let's take a look first at the idea behind finding an inverse. And we talk about this reversing or undoing idea all the time when we talk about inverses. So if we have the following action, and then we'll move to mathematical operations. I start off with a bare foot, and I should get a nice little clip art for this, but you know, it's Halloween time, so here we've got a broken, cut off foot, bare foot, and I put on my sock, and then I put on my shoe. So now I have my shoe on my foot. All right, I want to undo this. So where do I want to get back to? When I undo all this, what do I want to get back to? My bare foot, right? So I want to end up with my bare foot here, right? You can see why I wasn't an art major. Okay, so how do I undo this first series of actions? I took two actions here, 1, 2. How do I undo it? Am I recording? I don't think I am. Am I? Oh, good, I am. Okay. So how do I undo this series of two actions here on my foot? You take off the shoe. So the last thing you did, putting on the shoe, is the first thing you undo. This is exactly what you do when you create an inverse situation. You undo the last thing you did. So the first thing I'm going to do in my undoing is to take off my shoe. And then the last thing I do is to undo the very first thing I did. My first thing was to put on my sock. Now I'm going to take off my sock. And lo and behold, I'm right back to my bare foot. Cool. So what we notice here is that when we're trying to reverse a series of actions, those series of actions were originally done in a particular order. And we're going to undo each action by doing its inverse, but we just don't undo the action, we reverse the order of the original action. So let's do this with a mathematical operations. So my mathematical operation, let's suppose I was subtracting 9 from a particular value, or in this case, subtracting 9 from x. And then I'm multiplying the result. So I start off with x. I'm going to put that first. That's like my bare foot. I subtract 9 from x, and I have a result called x minus 9, and I think about that in parentheses. And then I multiply the result by 5. So what do I end up looking like? I end up looking like this. X take away 9 multiplied by 5. Notice how the word result gets translated into the mathematics. That's with the parentheses. Because if we had a number like 12, we would say 12 take away 9, and we'd replace it with one single number, 3. But in general, because we don't know the value of x, and we subtract 9, and since this whole result is being multiplied by 5, we must put it in parentheses. Okay, so I want to get back to my x. I want to get back to my x. So how do I get back to my x? Okay, I want to undo the last thing I did. The last thing I did was to multiply by 5. So now that's going to be the first thing I undo, which is I'm going to undo that by dividing by 5. So let's do it to x as we write each step. So here's my x. I'm going to divide it by 5. Here we go. All right. Then the last thing I do is I undo my first action. My first action was subtracting 9. So to undo that, I'm going to add 9 to the result. So here's my result. I put it in parentheses. I don't have to, but it's always nice to show your result from each step. And there I am. This is called the inverse of subtracting 9 from x and multiplying by 5. So if this was originally called f of x, this would be f inverse of x. You have just found your inverse function mathematically, without any series of steps read from a book, but simply by undoing each of the steps you performed, by reversing the order and undoing each one individually. Any questions on that? How we went from 5 times x minus 9 to its inverse? Both of these are linear functions. This is a straight line. So if you multiply this out, it'll be 5x minus 45. So it goes through 0, negative 45 is the y-intercept with a slope of 5. This is 1/5 x plus 9. So this is a line that has a slope of 1/5, and it goes through 0, 9. We can look at these pictures. You could throw these into your calculators and see what kind of pictures they make at some point if you're interested. Okay, so that's how we would we would sort of motivate the idea of undoing or reversing actions or operations. So remember when we did our very first example with our table of our nations and then the female literacy rate, when we had our nation as the input and our female literacy rate as the output, we defined that as a function. But when we swapped the order, we said we didn't get a function because 2 countries had 99 as the female literacy rate. So we had to call that a relation. So what we're going to concern ourselves with today is how can we tell whether a function has an inverse that's a function? Okay. So let's take a look at the following 2 functions. We have f of x equals x plus 1. Can you tell me which of these graphs is f of x equals x plus 1? The straight line. That's a linear function, right? This is a linear function. So the solution set for that entire function is represented by this graph. It has an infinite number of ordered pairs that will satisfy that equation. Every point on that line is a solution to that function. Okay, and therefore we're left with this beautiful little parabola. So this is our quadratic function, which has a shape of a parabola. And we know from all the work we've done in the last week on transformations that this parabola, if I were to do a quick sketch, looks just like x squared, but I'm just shifted to the right 1 unit. Okay, so notice I've taken 4 possible ordered pairs, 4 possible solutions from my straight line. Let's take a look at one of them. Negative 1, 0. Here's negative 1, 0. It's the x-intercept. That's a solution to that particular function. 1, 2 is right here. 1, 2, that's a solution. I just happen to randomly pick 4. Negative 2, negative 1. So I just picked 4 of them. We're going to swap the inputs and outputs like we did on Wednesday. And when we swap the inputs and outputs, we now have these 4 sets of ordered pairs. So if I asked you if this set of 4 ordered pairs represents a function, what would you say? Yes. Okay, because I see for every input, I have 1 and only 1 output. So a straight line will have an inverse, that's a function. Okay, straight line will have an inverse, that's a function. In fact, all increasing straight lines with a positive slope have a function. All straight lines with a negative slope have an inverse, that's a function. Okay, so another way to say that is all increasing functions. So whether you think of that as a straight line with a positive slope or like a cubic that looks like this, that's always increasing. So a cubic, straight line, something raised to the 5th power, all increasing functions have inverses that are functions. And you're going to see why in a second, well, maybe 2 minutes. And the same is true for decreasing, all decreasing and increasing functions. So when I say that, I mean that they're increasing over the entire domain or they're decreasing over the entire domain. So as you look at this function, the straight line, as you move from negative infinity to positive infinity, as x increases, so doesn't your output values over the entire domain. It doesn't go up and then go down and then come back up again. It's always increasing. Okay? So you could say that for functions that are always decreasing. Okay, so that's kind of one of those little always kinds of questions. All right, if I say to you, do always increasing functions have inverses? You can say yes. You got to be careful sometimes when we say the words always and never. But this is one case where you can say it's always true. All right, now let's look at our parabola. So let's take off these points. We're no longer concerned about the 4 possible solutions. And so if I plucked off 4 possible values from my quadratic that lie on that parabola, here they are. Here's 4 possible values: -2, 9, -1, 4, 0, 1, and 3, 4. And this parabola is definitely a function because if I drew any vertical line through this parabola, it would touch it in only one spot. So it's definitely a function, and it's okay to have a number like -1 go up to 4 and then have 3 go up to 4. It's okay to have different inputs go to the same output. Now let's switch them around. Let's swap them. And now let's take a look at our 4 ordered pairs. And what would you tell me about those 4 ordered pairs? Do those form a function? I'm telling you below that it doesn't, but can you tell me why it doesn't? Then 4 has 2 outputs, right? 4 goes to -1 and 3, and that would cause way too much confusion in the real world of mathematics and also in our world. 4 has 2 outputs. So it's definitely not a function. We would just say the inverse of this thing is a relation. And we're going to be focusing solely on inverse functions. Okay, so again, we're still doing this swapping of inputs and outputs idea, and we kind of want to move away from that and become a little more multi-dimensional here. So let's take a look at this idea, but let's take a look at a visual approach to the idea we just saw with swapping the inputs and outputs. So here are 2 functions, and so the question that lies before us is, can we look at the graph of a function and tell if it has an inverse? And the answer to that question is yes, we can look at the graph of a function and tell if it has an inverse. And let's take a look at how we do that. So somehow we've got to get some way of determining, let's see, with my straight line, I saw that once I swapped the outputs and inputs, or inputs and outputs, whatever order, it was a function. But with my parabola, it wasn't. And what can I do visually that's going to say one of those will be a function and one of those will not be a function? I don't want to have to plot points all the time and swap their coordinates. So the real nice way of doing that is to take a horizontal line. In this case, I'm using the line y = 4. And the reason for that is right here what we noticed, that 4, the output of 4 came from 2 inputs that were different. See, originally 4 came from a -1 and 4 came from a 3, and that's fine, that's perfectly legitimate. But now we want to see, why does that not work when I want an inverse function? So I'm going to draw a horizontal line straight through y = 4. Okay. And I noticed that if I can just sort of remove the picture of that parabola for a minute and just focus on the straight line, maybe if I make the straight line green, I see that my horizontal line intersects the graph of the function f in just one spot. So it only intersects it once. Now, if I sort of try to remove that from my vision, that green line, and focus solely on G, the graph of G, which is this really nice little parabola that's just been shifted to the right once, 1 unit. And now I look at how many times that red horizontal line crosses it. My answer is what? Excuse me? Twice. So I've got different answers. It must have something to do with why one has an inverse function and the other one doesn't. And in fact, that is exactly the reason visually. Because for different, so let's focus on our parabola. I'm going to get down on my knees here. For different inputs, let's pick -1 and 3. For -1 and 3, I was very legitimate in saying I can be called as an output 4. That's okay to be a function. But now I'm at 4 and I want to go back to my original number. And the problem is I can't. On my green line, if I'm at 4, on my linear function, if I'm at 4, I can go right back and see where I came from, the number 3. No problem. But on my parabola, I have this output called 4, but I came from 2 different inputs. That can't happen if I want my inverse to be a function. So if I have 2 different inputs, I must get different outputs if I'm going to have an inverse that's a function. Okay? So a horizontal line will show us if that's true or not. So if we draw a horizontal line and it intersects our graph in more than one spot, that's going to tell us that we do not have an inverse function for that particular graph, that function. We do not have an inverse function. So someone in my first class said, but can't you do something to the original function so you can get an inverse function? And I said, there's always ways to go around things, right? We always find a way, maneuver. So there is going to be a way we can manipulate that first function somehow. It's called restricting the domain, so we can wind up with an inverse function. But for right now, we don't want to worry about that. So we refer to this visual test as a horizontal line test, okay? HLT, like BLT for short. Okay, so let's take a look at a situation where I give you 2 graphs, and in just a few short weeks, you're actually going to be able to tell me, even though this graph looks pretty complicated in A, it's got a low point, a relative minimum, and then this relative maximum. It's got these hills and hills and valleys, and if I said to you that in about 2 weeks time period, you're going to be actually able to come up with the equation for that graph pretty quickly, you'd probably say, no way, Kavanaugh, but you will. It's not that bad either. So here's a graph. It's a polynomial function, okay? If I asked you on your quiz, your next quiz or your test, if that function had an inverse function, what would you say, Shane? Yes. Everybody agree with Shane? Wait, are you disagreeing with yourself? You are disagreeing with yourself? Why did you decide to disagree with yourself? Oh, because you just did that horizontal line test, right? Yeah, if you do a horizontal line test, you draw any horizontal line through here. In fact, this one that I draw doesn't hit it twice, it hits it what? 3 times, right? So this is thrice. No, I'm teasing. Once, twice, thrice, and 3 times, right? So this definitely does not, no way does this have an inverse function. Okay, now this next picture didn't come out well when I changed this to Smart Notebook, but you have a really nice visual graph of this at your seats. It looks something like this. So what about this function? Would this have an inverse function? Yes, because if I draw a horizontal line through here, it's going to hit it once, no matter where I draw my horizontal line. So this is a yes. So the way we write this idea mathematically is we say a function passes the horizontal line test if the following conditions are met. If you pick two values of x from your domain that are not equal, then the outputs f of x1 cannot equal f of x2. So we saw with our parabola that if we picked -1 and 3, those two numbers are not equal to each other, but yet their outputs were both 4. So that's why it failed the horizontal line test. So different inputs result with different outputs. That's another way to say what this mathematics says. We also call functions that have this particular property one-to-one functions. If you have a different input and different inputs, and that gives you different outputs, then we say the function is one-to-one. And every, here's the word every, here's one of those other almost like always statements. Every one-to-one function has an inverse function. Every one-to-one function has an inverse function. Okay. So those are the visual tests you can do with graphs of functions to tell if they have an inverse function. Any questions on that? Let's move along and see how we now take a look at finding the inverse of a function if it's defined by an equation. So far we haven't really found inverses of functions defined by equations. They've either been in tabular form, or I've given you a series of ordered pairs. So let's find our inverse algebraically. Okay, now we know that we've been able to interchange the x's and y's. So you would think that somewhere in the strategy of finding your inverse function, you would be switching your x and y values. And in fact, your author came up with kind of a clever little name for this strategy. It's called the switch and solve. Okay, so somewhere along the line, to find an inverse, you've got to switch or interchange your x, y values, and then you're going to solve your equation. So let's take a look at this procedure for the function 5x minus 6. Now, real quick in your mind, before you ever start, you want to put this in your notes because I didn't put it in there. Before you even start with step 1, right? Step 0, you want to do some kind of visual, either with your graphing calculator or if you know from looking at the function, is your function one-to-one? So you don't want to do all this work if you're not going to come out to have an inverse function. Okay. Now we know we did this little thing in class a few weeks ago where you solve an equation for y. And if you have a plus and minus, right, then you know there's going to be problems. So that's why your author didn't give you this step originally, because your author wants you to determine once you solve for y if it's going to have a one-to-one relationship. Okay, so here's our function. In your mind, can you see this function 5x minus 6, f of x equals 5x minus 6? Can you see it without throwing it in your calculator? Okay, what kind of function is it? Linear, right? And is it always increasing or always decreasing? It's always increasing. So this is a linear function that's always increasing. Okay, and since it's always increasing, every different input will have different outputs, and I know it will have an inverse function. So I'm feeling really confident. Yes, inverse function. So now I'm just going to follow a series of steps, and these steps work all the time. So you start off with your function f of x equals 5x minus 6. And since we've been talking about interchanging the role of x and y, let's first start off by replacing f of x with a y. That's the first step. And now I'm going to interchange x and y. So where I see y, I'm going to put an x. And where I see x, I'm going to put a y. And now I'm going to just solve this. I'm going to undo this equation. So that means solve it for y. So the first thing I would do to solve this equation for y is to add 6 to both sides. And that would give me 5y. And since x plus 6 is more than one term, I'm going to put that in parentheses. That would be my result. And now to finish this off, I'm going to divide both sides by 5, and I get y equals x plus 6 divided by 5. And the last thing I want to do is I want to represent that as a function of x. I know it's a function of x, and I also know it's the inverse. So I replace y with the notation f inverse of x. And lo and behold, this is how I undo my function 5x take away 6. I add 6, and then I divide by 5. We could have done that without the steps, but these can get a little funky, so it's always nice to have a series of steps. Okay. So you might feel proud of yourself, and you may not feel like you have to check your work, but I'm going to always ask you on a quiz or a test to verify that your function, your inverse function, truly is the inverse function. And this is the really big idea, Austin, right? The really big idea that you have to know right here. You have to be able to compose f with its inverse in both directions and come back to x. So let's do that. So I want tables 1 and 2 and half of 3, that's Austin and Ricky. I want tables 1 and 2 and Austin and Ricky to do this composition and see if it comes back to x. And you 8 people have to verify with each other. And then I want Sam and Buddha and the other 5 of you, tables 4 and 5, to do composition in this order and check with each other. Each half of the class has confirmed that when you put your inverse function, when you compose it with your function f, you come back to x. And when you take your function f and compose it with its inverse, you also come back to f. That's how you verify that these are inverse functions. Okay. So let's take a look at finding the inverse for this function right here. Okay, so you could try to do that little action and undoing the action. What's happened to x off on the side of your paper? It works. What's happened to x? What's the first thing that's happened to x? We've cubed it. And then what did you do to x? You added 1. Now we're going to undo it. So the first thing we're going to do is subtract 1. So we're going to undo what's happened by subtracting 1. And then what? Cube root, right? Okay. So let's do it through our series of steps that were outlined and see if we get exactly what we ended up with by just looking at each action and undoing it. So we replace f of x with y. We do our switcheroo. We make y x and x y. And now we're going to solve this equation for y. To solve that equation for y, notice you're going to undo each of the steps that originally happened to x. So the first thing I do is I subtract 1 from both sides, and I get x minus 1, and I put that in parentheses, equals y cubed. And now to get back to my original y, I have to take the cubed root of both sides, but anytime I'm working with an odd root, I don't have to pay attention to plus or minus. It's only when I'm working with even roots. So I take the cubed root of x minus 1, and voila, I get my y. And now to finish this off, I put it in functional notation, so I replace y with f inverse of x, and there I am. There is my inverse function. And to verify, you would do that composition both ways. Okay? So it is for many of these that, well, the ones you'll have for homework, they're fairly straightforward, but you can get some really funky things, and you'll have some of those in your group activities. And I've specifically said to you, do not try to do these algebraically, because you're going to learn how to do them graphically. So if you have an equation of a function that's a real nightmare to try to get to the inverse function, you can find you can get a quick sketch of the inverse functions by looking at the following idea. So here's a function that you may or may not know depending on your math background. We certainly know it's not a straight line. It's not a parabola. It's not anything that you've probably seen so far in the class. You will see a function like this the last couple weeks of class. Does anybody know what type of function this is? From any of their previous? It's okay if you don't. I'm just curious. Yeah, it could. It's not our reciprocal function because remember our reciprocal function has two parts to it, right? But okay, that's all right. So because the coordinates of the ordered pairs of our inverse function are the ordered pairs of our original function just reversed, we can do a real nice quick sketch of our original function and find its inverse by just picking a few ordered pairs that lie, few solutions that lie on that graph, and switching the role of x and y. So let's find a few nice points on the graph of f. And this is why would you, right now, so because it will probably take you 30 seconds to make a lot of noise, pull out one ruler from that little toolkit there, that little box, the craft box. Some of you may have more than one ruler, but everybody has at least one ruler. And have everybody at your table, please select a color different than whatever instrument or tool you're using right now. If you're using a pencil, okay, so there's highlighters in there, there's colored pencils, there's lots of different objects, so just select something, okay? All right. And then please shut the lid so that we're not making lots of noise. So notice I've started some work off with you here. You see this graph of f, and then you see this line on your Cartesian coordinate plane. Does anybody know the equation for this line right here? Y equals x, right? It's just your identity function. If x is 1, y looks the same, 1. If x is -2, y looks the same, -2. We call it the identity function. Okay, so we're going to pick some nice points. So go around and ask each table. Can table number 1 tell me a nice point that lies on the graph of f? Something that you can look at and get the coordinates right away. The graph of f. It says, given that the function f is graphed below. Okay, so we know it's not the dotted line. That's y equals x. 1, 2. So let's see. Yep, that's a nice easy point. 1, 2. Okay, table 2, another one. 2, 4. So it probably would have helped, Shane, if I labeled my graph, right? Like I told you to do, right? Yeah, look at that. I'm bad. What did you say? Excuse me? 2, 4. So I guess today you say my bad, right? When that happens? My bad. Okay, my bad. Okay, and table 3? 0, 1. Perfectly nice point. And hopefully we'll have 5 of them, but we may not. Table 4? 3, 8. And I think that's about all that we're going to get out of this. That's really nice, right? Okay. So now we'll start with table 5. Can you now list the coordinate points of the graph of the inverse? So can you tell me one point that's going to lie on the inverse of f? 1, 0, because you're just going to swap the roles of the x and y's. And back to table number 4, can you give me another point that's going to lie on the graph of f inverse? 2, 1, right? We swap the role, we get 2, 1. And then we get 4, 2, and then 8, 3. So now you just plot those 4 points. I'm going to use a different color. So 2, 1, 2, 1, 4, 2, 1, 0, 8, 3. And I see that if I connect those points, I start to go off in that direction. Now, how do I finish this off? I notice that for all of the negative x's after -1, I'm getting really close to 0, y being 0. So that means all these x values that are negative and all my y values that are really close to 0 are now going to swap rows. So now all my x values are going to be really close to 0, and all my y values are going to get really close to the y-axis. So this is a graph of F inverse. So using some of the language from one of our earlier classes, we say that F inverse and F have symmetry around this line y equals x. In other words, if you folded this paper right along y equals x, every point on F would have a point, a mirror point right on the other side. And the way we look at that mathematically is if you were to draw a line between 0, 1 and 1, 0, the distance from the point to the line y equals x would be the same. They'd be congruent. So these distances are always the same. Okay. So when you're just trying to get a quick sketch and visually see how to draw these, and you don't want to have to do a ton of points, look at where your point is and think about getting a point on the other side of this line the same distance away. So that's how you do a nice quick sketch to find the inverse function. So if you had something like this, which is a piecewise function, you want to pull out your ruler, and the first thing you're going to want to do is you're going to want to sketch, right, a real quick sketch of y equals x, or f of x equals x. You do a real quick sketch of it, do a nice color that's different, do a dotted line perhaps through there, dotted line. Okay. And some of you have the incredible talent of being able to look at the graph of f, and already you can see how to reflect that graph over the line y equals x, and you can visualize it right now. Other folks like me, we have to plot along with the points. We don't necessarily see it right away, but practice helps. After doing this for a long time, I can do it a lot better than I did originally. I think that's true about most things. So you could pluck off some points from your original function, but if you're really, got that talent that I just talked about, you might be able to do it right away. So I'm going to swap my inputs and outputs to get a graph. So this is f, and this is f inverse. So -2, -3, -2, -3, there I am. And if you compare these 2 points, yeah, you can see that they're equidistant from the line y equals x. And then you have the point 0, 1. And then you have the point 2, 4. But if that's not enough, you try to graph some other points. So what's going to happen here? And over here you say, well, does that look like -2, -1 to you? I think that's a nice point, -2, -1. So we've got -1, -2. Okay, so it looks like I'm just sort of following along here. This was -1, 0. So now I've got 0, -1. So this side runs parallel. Oh, I should probably put this in a different color, right? So here I am running parallel. Problem is I put this point, what's this point? 0, 1. I think I misplotted that. Is that supposed to be there? So now, where do I go? How do I finish this off? Any ideas? Well, you could just sort of look at where it crosses the y-axis and see where it's going to cross the x-axis. So it looks like about a half, 0, 1/2, or a little less than a half. So you go here, you put a point, and then you've kind of got your target to start to finish your graphs. Like this. So there's my inverse function. And that certainly looks like it's symmetrical about that green line. Here we go. All right. So you're going to have lots of practice today doing this. In about 5 minutes, you're going to have a zillion of these to do. Any questions before we move on? Okay, so let's go back to the question about how do we find the inverse of a function that is not 1-to-1. So here's here's the function. That's just something wrong here. This is wrong. Here's the function f of x equals x squared minus 1, and it should say, I just made a typo when I was making these lecture notes up yesterday. That should say, find the inverse of what? I got to change this. F of x equals x squared minus 1 if x is greater than or equal to 0. So it shouldn't say x squared. It should say x squared minus 1. Okay, so what are we doing here? The function x squared minus 1, the domain for this function right here, the domain for this function is from negative infinity to infinity. There's no problem. You can be any x value in the world. But if I use all of those x values, I can't get an inverse function. So what you do is you take half of it away. You literally remove this whole thing. It's gone. Okay? That's called restricting the domain. So how did I restrict the domain? I just took the red part of the parabola, which is from 0 to positive infinity. It's all numbers from 0 to positive infinity. So I can find an inverse of this function now if I restrict the domain. If I say I'm only looking at all the values from 0 to positive infinity, so we write it like that with an inequality. We write it like this in interval notation. Then it's always increasing. Woohoo! And if I use the horizontal line, it's only going to touch it in one spot. Okay, so let's go ahead and find the inverse of this. I replace f of x with y. First of all, before I even start, what's the range of the red side of this parabola? What is the range? Here's the domain, the restricted domain. Restricted domain. What's the range of that function? That restricted one. What's the range of that red part of the graph? -1 to infinity. So, what's going to be the domain of our inverse function? What's the domain of our inverse function? Right. Remember, they switch roles. So whatever I end up with here, when I write my inverse function here, off on the side, I have to say if x is greater than or equal to -1. In other words, the range now becomes my domain. All right. So we go ahead, we replace f of x with y. We saw, oh, then we got to switch our roles. So x is going to come here and y is going to come here. And now we're going to undo it. We're going to solve for y. So the first thing I would do is add 1 to both sides. And I get y squared. And then when I undo y squared, I get the square root, the plus or minus square root of x plus 1. But since I'm only looking at values of x that were originally positive, I'm only interested in the positive square root. So there is my inverse function. It's the square root of x plus 1 with this domain from -1 to infinity. So I go here, -1, 0, and I look like this. I probably cross right there. Okay? So that's what the inverse function looks like, and it's shown to you directly below. So the only problem I have with this is that they didn't put the domain on this. So you want to put here when x is greater than or equal to -1. So if you restrict your original function, be clearly identify the domain, if you want full credit, of your inverse function. Okay? So even on your handout that you're about to do, if your inverse function has a restricted domain, you might as well put that on so you get used to the habit. Okay, so you have about 5 or 6 or 7 of very playful, fun activities to do. So I've given you sketches of a bunch of different functions. I've asked you to sketch the inverse. So before you even start, go on every single one of those graphs and put in your line y equals x with some nice little color or dotted line. And then remember, For 5, 6, 7, and 8, I don't want you to find the equations for those. You can just do the graph of the inverse.